Welcome back. In the last part of this section, we're going to be talking about graphs of functions and also some basic shapes that we'll need to know in the future. So, of course, we know for a function, it has the property that every x value is used exactly once. So if you had a relation that was expressed as a graph, and if every vertical line crosses through that graph in only one place, that's telling you that an x value for that graph is being used only once. So for this little graph that I've drawn, every vertical line crosses through it in exactly one place, telling me that every x value only has one y value that matches up with it. That means that what I've drawn here, the little curvy line, that would be a function. On the other hand, if you had a graph where a vertical line crosses through it in more than one place, so for example, this vertical line crosses through twice, that's telling me that we have the x value being used twice, or in other words, for one x value, we have more than one y value. That would be something that's not a function. So for the vertical line test, we look at all the vertical lines that we could draw through our graph, and if vertical lines only cross through in one place, that means our y values are not being reused. That means it is a function. And if a vertical line crosses through in more than one place, that means our y values are being reused. This is not a function. Now, you can be a function, and you could also be a special kind of a function. So we had that relations were the more general category of things, and that functions are special kinds of relations. And we also have one-to-one functions, which are special kinds of functions. We're going to talk more about one-to-one functions in Chapter 3.7, but just for now, we need to know what they are and how to recognize them. So for a function, x values get used exactly once. And if it turns out that the y values also get used exactly once, then you have a function that's a one-to-one function. So the way that we can detect this is via a horizontal line test. So again, here I'm going to draw myself some sort of a curve. There we go. This for sure is a function because any vertical line that I draw goes through my graph in exactly one place. Is this a one-to-one function? The answer would be no, because when I look at a horizontal line, it can go through the graph in more than one place, meaning that my y values are being reused. Remember, for something to be a one-to-one function, it needs to be a function for starters. It needs to pass the vertical line test, but it also needs to pass the horizontal line test. Any horizontal line needs to go through it in exactly one place. So here's a graph of something that would be a one-to-one function. So here I'll draw a nice little sort of curvy kind of a line. For this, any vertical line is passing through it in exactly one place. So yes, it is a function. And if I think about any horizontal line that I draw through this graph, it will pass through in exactly one place as well, meaning that we only have y values being used once. So this would be something that's not just a function, it's a one-to-one function. So, vertical line test, do vertical lines pass through exactly once? If so, it's a function. Horizontal line test, do horizontal lines pass through exactly once? If it's a function and it passes the horizontal line test, then it's a one-to-one function. Of course, the big thing here is to be a one-to-one function, you first off have to be a function, which means that if you fail the vertical line test, you can't be one-to-one. So, for example, something like this shape, this is something that is not a function. It fails the vertical line test. So the fact that I can draw a horizontal line and go through this graph in exactly one place kind of doesn't matter. The fact is it's not a function, and if it's not a function, then it can't be a one-to-one function. So if we're thinking about sort of the order of things, we would need to check vertical line test first. Is it a function? And if the answer is yes, then we can check the horizontal line test to see if it's a one-to-one function also. So taking a look at some of these shapes, I start off with my first one, this sort of circular shape, and I can see for part A that definitely a vertical line crosses through this in more than one place, so sorry, not a function. And because it's not a function, there's no point checking to see whether it's one-to-one or not. B, this one, for sure, vertical lines pass through it exactly in one place, so it is a function. And if we're thinking about is it one-to-one, the answer is no, because a horizontal line doesn't cross through it in only one place, it crosses through in more than one place. So it's not one-to-one. C, vertical lines pass through it in exactly one place, so it's a function. Horizontal lines also pass through it in exactly one place, which means it's a one-to-one function. And D, the last one. Vertical lines pass through it in multiple places, so too bad for D, it is not a function. And because it's not a function, we don't bother to check to see if it's one-to-one or not, because to be one-to-one, you'd have to be a function first. So we've got B is a function, it's not one-to-one. C is a function, it is one-to-one. And A and D, both of those are not functions. All right. Last thing to talk about in this section are some basic shapes. We talked a little bit about graphing back in chapter 2, how we're not going to be graphing by taking a bunch of points that we make on a table of points and then plotting points and connecting the dots. Instead, we're going to be looking at graphing by using transformations. So we'll look at something and say, oh, this is the equation of a parabola that's been shifted to the left and moved downward, or it's had some other transformation done to it. So for us to be able to do that kind of graphing, we need to know what these basic shapes look like. So things that we're going to want to know for all of our little graphs that we have: what does it look like? What's its shape? What are the domain and range? And then for each of these graphs, there's at least 3 good points that we have. And later on, when we do our graphing by transformations, we'll be doing so by transforming those points. So when I have a parabola that's moved to the left by 1, I'll do that by taking all the points on a parabola and moving them all to the left by 1. And of course, in order to do that, I need to know what are the points. So we're going to take a look at all of these shapes that we have, our basic shapes. And there's a few that I have at the very end that we'll care about more later, but maybe not so much for right now. The first shape, this is just a straight line, y equals x, passing through the points 0, 0, 1, 1, and negative 1, negative 1. So if we're thinking about properties for this one, the domain is all real numbers for sure. And if you're thinking about the range for this one is also all real numbers. So I'm expressing all of my domains and ranges in interval notation. So my domain is from negative infinity to infinity, and my range is from negative infinity to infinity. We have our parabola shape, y equals x squared, and it's got 3 nice good points, negative 1, 1, 0, 0, and 1, 1. And I've got those nicely labeled on my graph. If I'm thinking for this, for domains and ranges, the domain is again all real numbers, and that the range for this is only values of y that are 0 and larger. So for my range, I'd say going from 0 to the far right. One thing that we're going to notice as we look at some of these shapes is that there's some repetition that goes on, that maybe the shapes are different, but the points and domains and ranges are kind of the same. So, for example, if we're looking at y equals x cubed, we'll notice it has exactly the same three good points that y equals x did. Negative 1, 1, 0, 0, 1, 1. Those are the same 3 points on y equals x cubed. And also the domain and range are the same. The domain is all real numbers. The range is all real numbers. So I could just make it a little bit shorter for myself here and just say this is the same as y equals x. Exactly the same properties for domains and ranges, and exactly same 3 points. Same thing with y equals cube root of x. This is looks kind of like y equals x cubed that's been turned on its side. You'll notice it has exactly those same 3 points, negative 1, negative 1, 0, 0, 1, 1. Its domain and range are also all real numbers, so properties for this one is also same as y equals x. So if we're trying to remember all of these three good points for all of our shapes, you're kind of getting 3 graphs for the price of 1. Negative 1, negative 1, 0, 0, 1, 1. Those would be your 3 good points for cube root of x. They're also your 3 good points for x cubed. They're also your 3 good points for y equals x. So we've got sort of some nice repetition going on here. We also have some repetition going on with y equals absolute value of x. You'll notice that the 3 points that we have here, these are the same 3 points that we had on our parabola. 1, 1, negative 1, 1, 0, 0. Those are also the same 3 points that we've got on absolute value of x. And same domain and range that we have here. All real numbers for our domain, and our range is just things that are 0 and larger. So if I'm saying what are my properties for absolute value of x, for domain and range, it's the same as y equals x squared. So if you know your 3 good points for y equals x squared, then you know your 3 good points for y equals absolute value of x. There is one shape that's got a different collection of 3 good points, and that's the square root function. So for square root of x, for sure, we're not going to be able to put any values of x in that are negative. So for our domain here, the domain is only things that are 0 and larger. And of course, when we square root a positive number, we're going to get a positive number out. So our range will also not involve anything negative. Our range only involves things that are also 0 and larger. So that has an impact on our 3 good points. For everybody else, we've had a negative 1 something showing up on our list of 3 good points. Of course, negative 1's not an x value we can use, so we're not going to have negative 1 comma anything. Instead, we've got 0, 0, 1, 1, and for my third point, I've chosen 4, 2, because I think it makes it a lot easier if we have 2 points where it's both integer values. If you chose 2 as your x value, then it would be square root of 2 as your y value, and that's maybe a little bit harder for us to deal with. So I've chosen 4 as my x value for my third basic point, and that's because square root of 4 is 2. So 0, 0, 1, 1, and 4, 2. Those are my 3 points for the square root function. There's 2 last little shapes, and I'm just going to mention them briefly, but I'm not going to go into too much detail about these now, because we're going to really be looking at these kinds of shapes when we get more into Chapter 5. We have the function 1 over x, and we've also got the function 1 over x squared, and these are different from everyone else that we've seen before. I'm just going to zoom in so that we can see things a little bit clearer here. You may notice if I'm zooming really far in that along my x-axis and my y-axis, there's actually a dashed red line that I have there. Same thing on the vertical axis. There's also a dashed red line. That is a vertical asymptote and a horizontal asymptote. For this graph, 1 over x, it's going to get closer and closer and closer to that y-axis without actually crossing it. My graph is becoming more and more vertical as we get closer to the origin. And the horizontal side of things, as we go further and further out for larger and larger values of x, my graph is getting closer and closer to being a horizontal line, y equals 0. So for this one, it's a little bit different. Number one, it doesn't pass through the origin at all, which everybody else we saw did. All of our other shapes, they all went through 0, 0, but this graph certainly won't, because 0 would be an excluded value. Instead, we're going to get close to the line x equals 0 and close to the line y equals 0. Same thing for 1 over x squared. It also has a horizontal asymptote of y equals 0. The graph is getting more and more horizontal as we're going further out. I know for the computer, the way that it's graphed it looks like it's almost starting to cross that line, but if we really zoom in, we can see no, it's not. It's just becoming more and more horizontal the further out I go. And same thing with the vertical side of things. As we get closer and closer to the y-axis, the graph gets closer and closer to becoming vertical. Again, this is not going to pass through the origin because 0 would be an excluded value. We're not going to do a whole lot of graphing with transformations of these, not in this chapter. We're going to really see these two shapes later on. I just want to do one little last bit, though, if I wanted to define what is the domain and range for these functions, because I think it's nice practice to use our interval notation here. For this, the domain is all the real numbers except for 0. The 0 is the one excluded value, so if I were to just say, what is my domain? It's everybody from the far left up to 0, not including it, together with everybody after 0 to the far right, again, not including the 0. So this would represent all the real numbers up to 0 and all the real numbers after 0. 0 is not included, so in other words, this is everything except for 0. And for my range, it's the same thing. I have all the y values, negative ones and positive ones. I just don't have 0 as a y value. So for my range, it's everyone from far left up to 0, together with everybody after 0 to the far right. For the 1 over x squared function, same thing for its domain. It's all the real numbers except for 0. So from far left up to 0, together with everybody after 0. For the range, my range is only positive values of y. There's no negative values going on here. So for my range, this would be all the numbers that are larger than 0, not including the 0.